This is example 2147 and it's a system of pulley, dashpot, and a spring. This is from our textbook, RAW. Here the system shown in the figure has a natural frequency of 5 Hz. For the following data, we have a mass of 10 kilograms. We have a pulley that has a mass moment of inertia about its center of 5 kilograms meters square. And then this pulley has two radius 1, which is the smallest one, where the dashpot is attached, of 10 centimeters. And then we have a bigger radius where the mass is attached of 25 centimeters. If we give the system an initial displacement, and we know that the amplitude at free vibration reduces in 80% in 10 cycles, we want to find the characteristics of the system. The characteristics of the systems are the constant of the spring and the constant of the dashpot, because we already have all the inertia values. Let me write down the data that we are given. We have the natural frequency, which is 5 Hz. That gives us a circular natural frequency, so 2 pi of the natural frequency, which is 2 pi 5 radians over seconds. Then we have the mass, that is 10 kilograms. And then we have the moment of inertia, which is 5 kilograms meters square, and both radius. One is 10 centimeters, which is 0.1 meters, and the bigger radius is 25 centimeters, which is 0.25 meters. We also know that at cycle 10, the amplitude decreases in 80% of the initial displacement. So we do not know the initial displacement, but we know the relationship between the displacement at cycle 10 and the initial displacement. So the displacement at cycle 10 is 0.20 the initial displacement. And we like to find the constant of the spring and the constant of the damper. Let's draw our free body diagrams. We have the tension of the rope. I'm going to draw a free body diagram for the mass and one for the pulley. So I cut the rope, right? And then I have the force of the spring that it opposes to the displacement. I have the two reactions produced by the pin at O, and I have the force of the dashpot. I don't draw the weight of the pulley because it's attached to O, right? So, and we will take moment about respect to point O. Now that we have the free body diagrams, let me write here that we will work with the angular displacement of the pulley, and that will be our main variable. So here we have two variables, x and theta, and we will write our equations of motion in terms of only one variable because the system has only 1 degree of freedom. I'm adding forces in x. This is negative the tension, negative the force of the spring equals to mass times acceleration. And as I said, I'm going to place the variable of linear displacement of the mass in terms of the angular displacement of the pulley. You see the point B has the same velocity as the mass, and that will be the dot times R2. Can substitute theta to x2 dots by R2 theta 2 dots, and I can substitute x by R2 times theta. Now let's take moment respect to the center of the pulley. The forces that create moment are the tension multiplied by R2 plus the force of the spring, which is the constant of the spring times the velocity of point A, which is theta dot R1, and that's equals to the mass moment of inertia times the angular velocity of the pulley. If I put everything in one side of the equation and I substitute the tension that we found in the other equation, we get everything in terms of only theta, theta dot, and theta 2 dots. And we can write it in terms of a term that multiplies the angular acceleration, a term that multiplies the angular velocity, and a term that multiplies the displacement. This is our equation of motion. To put it as in the typical form we're used to seeing, I will call what is multiply the acceleration, I will call equivalent mass. What multiplies the velocity, the angular velocity, I will call equivalent constant of the damper. And what multiplies the angular displacement, I will call it the equivalent constant of the spring. My equivalent mass is the mass moment of inertia plus R2 squared times mass. My equivalent damper is C times R1 squared. My equivalent constant of the spring is equals to K times R2 squared. In order to relate the amplitude at cycle 10 with the amplitude at the initial of the vibrating motion, we will use the logarithmic decrement. And if we have not two consecutive amplitudes in one cycle, but two amplitudes in a lapse time of 10 cycles, we use 1 over n logarithm of the amplitude 1 over the amplitude in that amount of cycles, in this case 10. It's 1 over 10 logarithm of x0 over 0.20 x0. That's 1 over 10 logarithm of 1 over 0.2, which is our decrement logarithm is 0.1609. We can relate our damping ratio, zeta, in terms of the logarithmic decrement. That is equals to logarithmic decrement divided by the square root of 2 pi squared plus logarithmic decrement square. I'm going to plug in the numbers and I get the zeta value for my system, which is 0.02561. That's an under-damped system, which was what we expected because the amplitude decreased over time and they talk about cycles. So we know that it's a vibrating system. The natural frequency of the system is defined as the square root of the constant of the spring divided by the mass. It's very important we here take the values of the equivalent constant of the spring divided by the equivalent constant of the mass, because this is composed in several terms. So here we can find the equivalent constant of the spring because we have the value for the natural frequency and we have all the parameters that define the inertia term, which is the equivalent mass, which is 5 plus the radius, which is 0.25 squared multiplied by 10. That gives me a value for the equivalent constant of the spring. I can divide that by R2 squared and I get the value for the constant of the spring. The constant of the spring is equals to 88826.44 newtons over meters. To get the characteristic of the damper, we will use the definition of zeta. You recall that zeta will be equals to the C equivalent divided by the critical constant of damping, which is 2 square root of K equivalent mass equivalent. So we solve for the equivalent constant of the damper, and we have zeta times 2 square root of the equivalent constant of the spring times the equivalent mass. Those values are up there in the bracket here in top. So let me substitute all the values. Zeta is equal to 0.02561 times 2, and the equivalent constant of stiffness is 5551.65. So my mass moment of inertia is 5 plus 10, which is the mass, times R2 squared, which is 0.25 squared. Now we get the value, and I get 9.05. And now I solve for C, which is that value divided by R1 squared. And that's equals to 905.0221 newtons seconds over meters. To get the characteristic of the damper,